Our first talk is comparing normal and binary d-optimal design of experiments by statistical power. Yes.
Hi, everyone. As was mentioned, my name is Addison, and I'm excited to be talking about comparing normal and binary d-optimal designs. The method that we'll be comparing them is by statistical power. So first, I want to start with a little bit of motivation. I had the opportunity to come work here at IDA last summer, and the question that was posed to me was, how should an operational test event be planned when the response of interest is a success or failure? In other words, if the response is binary. And for those that are not familiar with this operational test, a brief overview can be seen in this diagram here. So imagine we start with some sort of program of record. It could be a jet fighter or something else. And we want to answer a question about this program of record. We want to plan a test, actually carry out the test in the operational test event. That's where the data would be collected. And then from that data, perform some sort of data analysis, making inference or some sort of conclusion. Now, in the data analysis, when we get the response, we know it's already, before we've even planned our test, we know it's going to be binary in nature. And so the question is, well, how does that affect our test planning? So to partially answer this question, we compared two designs, the binary d-optimal design with the normal d-optimal design. And here are some of the key findings that we found. So we compared the binary d-optimal design with the normal d-optimal design. And as I mentioned before, we use statistical power to do that. Now, that's not as standard as some of these other type of design comparisons that I'll talk about. And the other type of design comparisons actually do favor the binary d-optimal design. But the surprising result that we found is when we were looking at statistical power was actually that the normal d-optimal design resulted in higher statistical power than the binary d-optimal design, despite using logistic regression in the data analysis. So just to make sure that we're all on the same page, design of experiment, when I say that, DOE, I just mean that's planning of an experiment with the statistical analysis in mind. When I say d-optimal, the binary d-optimal, d-optimality is a criterion, the optimality criterion that minimizes the generalized variance of the parameter estimates, or in other words, it makes sure that we have precision in what we believe on some sort of condition effects. So let's look at a hypothetical example. If we have an operational test event, and that's to be planned to explore the condition effects on torpedo hit probability against, say, an adversarial submarine boat, the response that we'd be interested in recording would be, did the torpedo hit or miss the target boat? So this is binary in nature here. So first, when we're comparing these two designs, the normal d-optimal design, as is stated in the name, anticipates normal data in the collection, where the binary d-optimal design anticipates the binary data. Both, because they're d-optimal, will optimize the precision of the parameter estimates, but based on either the normal or the binary assumptions, respectively. Once you create your two designs, you'll go to collect the data. Both will actually collect a binary response in the two different designs. And then in this case, we'll use logistic regression to analyze the binary data in both cases. That way we know that we're comparing them on fair terms. So let's take a look at a notional example of how these two designs would come out. So the binary design over here in black, let's say that we had three condition effects that we were interested in. The speed of the target boat, maybe the location of the target boat, was this in deep or shallow water, and then was it employing evasive maneuvers or not? So we have two categorical and one continuous factor here. The size of these spheres represents the proportion of runs that we would run the test under a certain factor configuration. And something that you'll notice right away, the binary design has 7 support points, whereas the normal design has 8 support points. And then the binary design has different sizes for each of those factor configurations that it has, where the normal design is all equal. So standard design of experiment comparisons, including the d-efficiency ratio and the fraction design space plots, both favor the binary design. Something to note about that, though, is both of those comparisons do rely on asymptotic theory, or in other words, assuming that your sample size is very large. Now, here's the surprise. When you look at the statistical power, you'll see that the binary design actually underperforms the normal design in terms of statistical power. So you have sample size here on the x-axis, power on the y-axis. The normal design is illustrated here in the red, and the binary is in black. And you can see for each of those sample sizes, the normal design outperforms the binary design. Now, of course, this is just one example. We looked at many, but you can see here that the binary underperforms the normal. So, sort of in summary, the normal de-optimal design outperforms the binary de-optimal design, despite using logistic regression in the data analysis. In other words, we're giving the favor to the binary design, but still the normal design outperforms. And in some ways, this should be good news. I think most people, when they're doing a de-optimal type of design, would use a normal de-optimal design, and they might not know that. They might not specify it with the normal, but you use a de-optimal more frequently. And so what we're saying here is that the normal de-optimal design, if the practitioner is interested in primarily in power, the normal design outperforms the binary design. So we did mention, though, that the standard design of experiment comparisons favored the de-optimal design, and this has motivated people to research more into that. And then a few steps that we're looking at now is considering, well, what about a different type of optimality criterion? There's a whole alphabet. D is just one that we are looking at. And then also, we want to better understand why it is that the normal design is outperforming the binary design, despite the binary correctly anticipating the type of data that we'll be using. Thank you.
So we do actually have time for a question, if there's a question for our first speaker.
Binary de-optimal design, did you make an assumption of what you thought the coefficients of your logistic regression model would be?
Exactly. That's a great question. So when we did the binary de-optimal design, we did locally optimal, meaning that we had to anticipate what we thought the coefficients were. I wanted to give the binary de-optimal design the advantage and see that the normal design was outperforming. And so we actually used the exact coefficients in the simulation. And despite actually giving the advantage of using the coefficients that were the actual parameters, the normal still outperformed.